You design a rocket. Nice. So to win this competition, it needs to travel the highest and be safely recovered by the use of a self-deployed parachute. So question A, it starts from rest on the launch pad, meaning it has a speed of 0, it's stationary, and it reaches a maximum height of 64 meters, and it takes 3.6 seconds to reach that height. Calculate its average speed, I guess it should say during this time. So what is the average speed as it goes from the ground to its maximum height? Well, let's see what we're given. We're given a maximum height. We're given a time. We aren't given a starting height, but when it says like on the launch pad, we could assume that it starts at 0 meters. Right, that's a fair assumption. If it didn't, the question would need to give that information to us unless it's something we were like solving for. So it goes from 0 meters up to 64 meters in 3.6 seconds. So average speed, V average, is the total distance divided by the total time. And the total distance the rocket traveled was 64 meters in 3.6 seconds. So the average speed is, menu, run, 64 divided by 3.6 to give 17.777 meters per second. Great. Now, in physics and in science, we round our final answer to the lowest number of significant figures given in the question. So what I mean by that is the height is 2 sig fig. The time is also 2 significant figures. So our answer needs to be rounded to 2 significant figures, which would be 18 meters per second. And in brackets, we can put 2s.f, just to note that we've rounded our answer. All right, to keep it in line with the accuracy of the parameters in the question. Sweet, so that is average speed. Total distance over total time. Cool, and we're also told in question B, as it expelled its fuel, so it's a CO2 canister, right, pressurized, and as the pressure is different to the outside air pressure, the air or the CO2 will flow out. That is its fuel, and it accelerated. So from rest, we know that means 0 meters per second, up to 20 meters per second in a time of 1.5 seconds. And it's asked us to calculate its acceleration. Well, we know that acceleration is the change in speed over change in time. Right, how much speed we gain and how long it took us to gain that speed. And if you're wondering what that triangle is, that's capital delta, so Greek letter delta, and it means change in. So how has the speed changed? Well, it would be its final minus initial speed. Final minus initial. In this case, our final speed is 20, our initial speed is 0, and the time it took is 1.5 seconds. Right, it's gained 20 meters per second of speed in 1.5 seconds. So simply that's 20 divided by 1.5. And I did the minus 0 just to show, in case that it was already moving, right? That wouldn't necessarily be 0. So computing that, 20 divided by 1.5, 13.3 reoccurring. Like before, we need to round it to the correct number of significant figures. So looking at the question, time, 1.5, that is 2 significant figures. Speed, that is actually only 1 significant figure. right? If it was 20 and then a point, that would be 2. But since it's 2, 0, the 0 is insignificant, and we will round our final answer to 1 significant figures. Keeping in mind the units, acceleration, meters per second, right? Change in speed per time. Alright, question C. Describe the rocket's motion after it ran out of fuel, but before it reached its maximum height. So here we go, let's follow along, let's go on the rocket's journey. So it starts on the launch pad, it accelerates, right, it uses its fuel, and at this point, the fuel runs out. Well, it's gained lots of speed, so its momentum actually carries it forward a bit before it reaches its maximum height, and then falls back down. Cool. So, what's going to happen in that red section? So, a few things we could say. So, describing its motion, let's start with what direction it's traveling. So, it is moving upwards, right? And that's because it hasn't reached its maximum height yet. So, in other words, its speed, or let's use the word velocity to indicate it's a vector with direction. Velocity is up. Right, it's moving upwards. Well, it's run out of fuel, so it's actually not accelerating upwards anymore. What's happening with its acceleration? Since it has mass, and we're assuming this is on Earth, right? Gravity will be acting on that mass to provide a weight force downward. So it is actually accelerating downwards, right? Or you could say it's decelerating upwards, right? Same thing. In other words, it is losing speed. For example, if it was moving at 20 meters per second when the fuel ran out, every second it loses 9.8 meters per second due to acceleration due to gravity acting downwards. Cool. Is there anything else we could say? So moving upwards, however it's accelerating downwards. No. Yep, that's good. And in the next question, or the third question I believe, drawing free body diagrams really helps describe this motion. Cool. But describing motion, make sure you comment on velocity and acceleration. Cool. Alright, question D. After reaching its maximum height, the rocket begins to fall down. Okay, so that's this green section here, that green arrow, it's falling down. It reaches a speed of 12.6 meters per second before deploying its parachute. Now, as it deploys its parachute, it decelerates at 7.6 meters per second squared for 0.8 seconds. Calculate its new terminal velocity. Cool. So, it's initially moving down at 12.6 meters per second. That's the initial speed. We are also told it decelerates at 7.6 meters per second squared. In 0.8 seconds. And it's asking us to find the new speed. Cool. So, a few ways we can approach this. Looking at these, we have 3 knowns and 1 unknown. So we could use a kinematics equation. So in your formula book, looking at the kinematics equations, or we could actually use the equation we already used in question B, which is acceleration is the final minus the initial velocity over time, and we are solving for final. We are given initial, we are given time, and we are given acceleration. Right? And actually this is how some of the kinematics equations are derived from this relationship. So let's just use this one. So I will rearrange first and then substitute in the values. Actually, no, I won't. I'll show you how you can do this on your calculator very easily. So substituting in the values, 7.6 for acceleration, VF is our unknown, minus the initial speed, 12.6, over 0.8. So from here, you can solve it, which you should be able to do. However, sometimes you just want to make sure you're right. So on our calculator, we can go menu, went too far, equa for equation. We select F3, which is solver, and we input our equation. So 7.6 equals is shift dot, so near the bottom, shift dot equals, and now instead of VF, I don't have that button on my calculator, I will use, first I'll put a bracket, x minus 12.6, close bracket, divided by 0.8. Cool. So I put the numerator in brackets because it had two terms, divided by the denominator. I'll hit execute, and now you think, oh, x equals 0. No, you need to hit F6 to solve. X actually equals 18.68. Now, does that make sense? Not really, because it should have decelerated, right? So that tells us one of our signs is incorrect. Now, which sign is it? Initial, final. Did you spot it? So, some learnings from this. We can define down as positive, right? Or up. Let's just go down. Now, acceleration, 7.6. The question actually says that it decelerates, which means it's opposite to the velocity. So if we change A from 7.6 to negative 7.6, it tells us we'll be losing speed, right? Losing speed. So let's revise that. We can hit exit, exit again, go back to solver. Oh, hello. Oh, there we go. Using my arrow keys to, excuse me, get into the equation. So putting on negative, execute, solve. There we go. So our final speed, 6.52 meters per second. And again, let's round it to something sensible. So what's that? One significant figure. So that would round up to 7 meters per second. Just so to recap this question, question D, we were given an initial speed, an acceleration, which is actually negative compared to the speed because it's acting in the opposite direction. We were given a time and looking for the final velocity. So we listed out what we knew, being a bit careless initially, but catching it because we checked the answer and it just didn't make sense, that acceleration is actually negative. Or alternatively, we could have made the initial speed negative and it would have worked out as well. Right? As long as the speed was opposite acceleration in this case. And then we used our equation solver to find VF, or did it algebraically. See ya.